In this video, I'll be solving problem 3.52, which states the following. Go ahead and pause to read. And I'll be focusing on part A, this first part. Essentially, we want to prove that the quadrupole term in the multipole expansion can be written as this equation here. And it uses this definition for the quadrupole moment, which also uses this definition for the Kronecker delta here. And I went ahead and rewrote the equations on the right-hand side here. And it also refers to this notation of equation 1.31. And what this equation introduces is the idea that index 1 corresponds to x, index 2 corresponds to y, and index 3 corresponds to z. So I've written some examples here of how that would be used. And you'll also notice that when I've rewritten the quadrupole term and the quadrupole moment, I've underlined these vector quantities. And I'm going to be doing that throughout the rest of this problem, just so I can be really sure and communicate well what is a vector quantity and what is a scalar value. You'll notice that these r hat quantities do not have a underline underneath, and that's because we're not talking about the r hat vector. Instead, what this is referring to, and this is in pairing with equation 1.31, essentially writes out rx hat. If you could split the r hat vector into x, y, and z components, these values are what we're referring to, not the vector quantity. And on the left here, I've kind of got the problem started. I've rewritten this summation for simplicity's sake. I figured having these terms up front every single time could get a bit messy on the paper. And so I'm going to evaluate this summation alone and get down to the end, and I will plug those terms back in. Essentially, I've also plugged in our definition for the quadrupole moment in this line below. To continue evaluating this equation, I'm going to split up the summation up front. I'm also going to shorthand this row, just so I'm not having to write a vector quantity every line while solving this problem. But every time I write row here, I am referring to this value. All right, my next step, I'm going to look at these summations separately. So if we look at this first one, if I write this out explicitly, we'll get and you'll notice this is equal to r hat dot r prime vector. These are vectors. And this is also equal to r prime cos alpha, where alpha is the angle separating the two vectors. This is just the definition of a dot product. So a similar thing happens to this summation. And this final summation has a Kronecker delta within it. The Kronecker delta eliminates the cross terms. So essentially, we're getting r hat x plus r hat y, so on and so forth. And that is going to just simply be r hat dot r hat, which is equal to 1. So now that I've simplified that a little bit, I'm going to bring my equation back down and plug in these values that I've evaluated. So now I've simplified this a little bit, I'm going to plug it back into our quadrupole definition up here. Bring down this equation. And remember, what we evaluated here is what I'm underlined here in red. So now I'm going to plug that in. And I'm also going to factor out these r prime squareds. So now I'm going to write the general equation for the multiple expansion. So this is our general equation, and the quadrupole term refers to n equals 2. I'm going to evaluate at n equals 2. Again, I'm shorthanding rho, and we're using the definition of a Lagrange polynomial here. T sub 2 is equal to 1/2 multiplied by 3 cosine squared alpha minus 1 rho d tau. So now that I have this evaluated, we can compare, and you'll notice between these two equations, you just have to rearrange where this 1/2 is sitting, and they match, they are identical. So next I'm going to move on to part B. So part B states, find all 9 components of Qij for the configuration in figure 330. Assume square has sides A, lies on the xy plane, centered at the origin. So I brought the figure in here. We have the origin here, and we have side length A, and it lies on the xy plane. So I'm going to number these points, and that'll be helpful later. Brought down the definition of our quadrupole moment, so we can evaluate those 9 components. But first I'm going to figure out what we know about r prime for all cases. And you'll notice, let's say if we just look at number 2 here, just look at number 2, I can write r prime like such. We have a/2 in the x direction, a/2 in the y direction. And all other r primes are going to take this similar form, other than having like a plus or minus here, corresponding to whether you're going into the negative x or the negative y, or the positive x or the positive y. So because I know that, I also know that the z component for all r primes are going to be 0. So let's write that. Rz prime is always going to be equal to 0. And Rx prime squared is going to be equal to Ry prime squared. And that is going to be equal to a/2 squared. Remember, this is like a plus or minus depending on what point you're actually looking at. But once you square it, if there is a minus, it will go away. So we get a squared over 4. If we look at the magnitude for r prime, we're going to get, let's see, it's going to be some plus or minus a/2 squared, and then plus or minus a/2 squared, taking the square root of that. So this is going to turn out to be a/2 square root 2, no matter whether you're dealing with pluses or minuses. And so the magnitude of r prime squared is going to be equal to 2a squared over 4. And I'm keeping it not simplified, so that way it'll be easier to see what we're doing while we're computing these 9 components. When we're evaluating the cross terms, you'll notice that overall the magnitude is going to be the same. However, we don't know if these Rx and Rys are positive or negative. So we'll have a plus or minus a squared over 4. And say, for example, for, you can see this directly, such as for 2 and 3, since both the Rx and Ry terms match in sign, we're going to get a positive value. And for 1 and 4, they don't match in sign, so we're going to get a negative value. I also know that if we have any term here, let this be x or y, then multiplied by r prime z, this is going to equal 0, because the z component is equal to 0. So now that we have some general rules written down, some things we know about r prime, now we can evaluate the 9 components. Because we're dealing with discrete charges, something kind of interesting happens to this integral. I'm going to rewrite this with double primes. And I'll explain what I mean with the double primes in a second. And essentially, this double prime vector that I've defined is just a much more general expression for our source, where it spans all space. And this rho value, only where we're looking where the point charge isn't, it's going to go to 0. And where it is, it's going to be that plus or minus q, depending on what point charge we're looking at. And the way we represent this mathematically is with the Dirac delta function. So remember, we're integrating over all space. So what this Dirac delta function is basically saying is what I just stated, that rho is going to equal plus or minus q only at this r prime vector that I defined earlier, this discrete vector that doesn't span all space. The r double prime spans all space. So this integral, due to the Dirac delta function, just becomes the same thing, except we evaluate r double prime at r prime. So it becomes this general value that spans all space, and now we're evaluating it at only the points where our charge is. So I'm first going to evaluate the terms in which I equals j. So this will be our xx terms, our yy terms, and our zz terms. And I can rewrite this equation like such. Notice the Kronecker delta has turned to a 1 here because I is equal to j. And if you'll remember, the rx squared and ry prime squared are equal to each other, and they're both equal to a squared over 4. So I'm going to write that qxx and qyy are equal to each other. And that is equal to a squared over 4 in place here for the r prime I squared. And r prime, the magnitude squared, is, of course, 2 a squared over 4. And essentially, this is like a summation. So if I'm going to list the first point charge, or evaluate this for just the first point charge, remember we have a negative q here. So I would put a negative q. And if I continue to evaluate this for all charges, you'll notice that this term stays the same, no matter what point charge we're looking at. So instead of rewriting this term a million times, I'm instead just going to kind of factor it out, refactor it out, and write the point charges that we have. So we have 1 is a negative q, 2 is a positive q, 3 is positive, and 4 is negative. Matter of fact, I'm going to bring this figure down so we have it for reference. And you can see that this term here will go to 0, and therefore the terms qxx and qyy are equal to 0. Now, if I go to evaluate qzz, a similar thing happens, but I'll work it out. And r prime sub z, if you remember, is just 0. So that term, this first term here, becomes 0. So still have that magnitude of r prime squared. And again, this term is the same for all point charges. So I'm going to add them up at the end here. And again, that equals 0. Now for the case where I doesn't equal j, I'm going to evaluate this function again. And if you remember, the Kronecker delta is going to go to 0 since I does not equal j. Applying the facts that rz is equal to 0, anytime when I or j is equal to 3, or z as it corresponds to, so let's say like qxz, qyz, qzx, and qzy, those are all going to equal to 0. When going to evaluate qxy and qyx, these values are going to be equal to each other. And this is, you can prove this to yourself just by looking at this general equation that I wrote. Because if I and j were to switch, we would still just be multiplying j prime times ri prime, and we would evaluate the same answer. Now this 3/2 is going to be there for all of our point charges, but the ri, rj, and the plus or minus q is going to change depending on what point charge we're looking at. So if I bring this figure down, make it easier to look at, then we have for the first term, starting with the first point charge, we will get and you see all these places where I have a negative, they will cancel. So we get pluses here. Negatives cancel. And we have 4 of the same term added together. We have 3/2 times 4. And let's evaluate one of these terms. A squared over 4 times q. qxy and qyx are equal to 3/2 a squared times q. And that is all 9 components. You can count them up. We got 1, 2, 3, 4, 5, 6, 7, 8, 9. Excuse me, 7, 8, 9. Here it is. And that is all 9 of our terms. Most of them are 0. Actually, all of them are 0 except for qxy and qyx.